Thank you for the introduction. Thank you for the introduction. I'm Taiki Fukiage from NTT. I'll talk about perceptually based adaptive motion retargeting to animate real objects by light projection. So recently, as you know, recently there is growing interest in human perception, especially in research areas of this virtual reality and augmented reality. One reason for this is because understanding perception can lead to overcome difficult conditions constrained by physical constraints. For example, in the area of spatial augmented reality or projection mapping, many studies try to utilize the perceptual property of human visual system to control appearances beyond the projector's physical capability, such as dynamic range. And among them, previously we proposed an illusion-based light projection technique that adds the dynamic impression onto the surface of physically stationary object without changing its color or texture information. And we add this kind of luminance modulation onto the surface of real object. And this luminance modulation drives the motion detector in a visual system. The process to generate this motion-inducer pattern is really simple. We first capture an image of the projection target and then animate it in a computer based on the input motion vectors. Then we take difference between an animated frame and the original frame, and that gives the motion-inducer pattern. This simple strategy works because the human visual system analyzes visual motion from coarse dynamic luminance signals. Even though there are small discrepancies between motion signal and color and texture information, they are resolved at feature integration stage in the visual system. So the motion-inducer pattern consisting only of luminance signal effectively drives motion perception without changing color or texture information. And most importantly, because the projection of motion-inducer does not need to reproduce physically correct intensity of an animated frame, our technique works properly even under bright light condition, bright environmental light condition. However, in deformation lamps, there is a limitation in producible apparent shift sizes. So when we try to add too large motion, like in this example, it produces inconsistent perception. Moreover, because this technique relies on the visual illusion, these shift limits are dependent on the properties of the human visual system. So in order to obtain a good result, somehow we needed to manually adjust the shift sizes. But this manual process has prevented us from applying our technique to general motion retargeting framework, where the motion information is given in real time, or the motion sequence is so long that manually adjusting parameter for each frame is not practical. So in this work, we overcome this issue by automatically optimizing input motion vectors by using the perceptual model. And based on this perceptual model, we adaptively retarget the input vectors so that we can obtain maximum motion size within perceptually acceptable range. From here, let me focus on how we designed this perceptual model. The basic idea of our perceptual model is that the shift limit can be determined based on the perceptual distance between projection result and its ideal appearance. To obtain a projection result, we simulate whole projection process in a computer. To obtain the ideal appearance, we simply warp the original image using the input motion vector. However, usually under the bright environmental light, the projection of motion-inducer does not produce as large motion impression as the sizes in the input vectors. So we need to consider the perceived deformation size. So here we introduce an additional parameter alpha that scales input vectors to make the vector size as close as the perceived level. And we jointly estimate this perceived deformation size as well as the subjective inconsistency by finding an optimal alpha that minimizes the perceptual distance. Okay, let me explain how we compute the perceptual distance. To compute the perceptual distance, we took a similar approach to many previous works on image quality assessment, where the objective is to predict subjective image quality of a distorted image given the reference image. And one of the standard way to estimate image quality is to use a computational model of low-level visual mechanisms in the human visual system. In this case, usually input images are both transformed into model representation, and then distances in this representation is used to estimate the the distances in this representation is used to as an estimate of image degradation. So in our case, we transform the ideal appearance and the projection result into the model representation, and we use the minimum distance in this representation as an estimate of subjective inconsistency. And here I show the model representation we used to compute the distance. And it consists of several stages. The first stage simulates the local luminance adaptation, and the second stage decomposes the image into several different spatial frequency bands using Laplacian pyramid. And then each spatial frequency band is processed by linear gain to simulate sensitivities of the human visual system to each spatial frequency. And finally, these values are processed by nonlinear transducer to simulate the contrast gain control process. Okay, next, let me explain the psychophysical experiment. So we examined how well the perceptual model can explain the actual subjective experience. And this is the general setup of the experiment. And this is the typical example of stimuli. We projected this kind of luminance modulation as motion-inducer pattern. And in the first task, we measured the subjective inconsistency. So we asked the observers to answer whether the projected patterns naturally merged with the printed image. And in the second task, we measured the perceived deformation sizes. In this task, the pixel warping movie of the printed image is presented on the left side, and the observers were asked to match the deformation size of this reference with the deformation size of the projection result on the right side. And the data were collected from 10 target images, 9 deformation sizes, 2 deformation patterns, and 4 contrast levels. So there were in total 720 conditions. And 10 participants participated in the experiment. And this is the prediction result for the task 1, the subjective inconsistency. And each data point represents each condition. As shown here, the data points are concentrated around the regression line, indicating that the prediction accuracy is quite good. And this is the result for the perceived deformation size. Again, we found that the prediction accuracy of this model for this task was quite high. So now we obtain a good perceptual model to predict the subjective inconsistency. The next step is to optimize the input motion vectors based on this model. The basic idea of our method is quite simple. We just rescale the input motion vectors so that the subjective inconsistency obtained from the model stays within a tolerable range. And we measured this tolerable range in another user study. But here, the best scaling factor depends on the local image structure we conduct this optimization process for each spatial area. However, with this strategy, when the input motion involves like rigid motion, locally modulating this vector length may significantly change the perceived impression for that motion structure. So to address this problem, we divided the optimization process in two paths. We initially decreased the vector length with spatio-temporally smoothed scaling factors so that the scaling process does not violate the original motion structure. Then, in the second pass, we extract only the high-frequency component of the motion vectors and optimize the scaling factor for this component in the same way. However, with this time, we allow larger spatial variation of scaling factors to obtain locally optimized results. Okay, now I will show some results. And this is the result of facial motion retargeting to real picture. However, without optimization, you see some visible deviation or inconsistent perception. But after optimization, we get more natural results. And this is another example. Oh, sorry. So without optimization, you see some inconsistency around here. But with optimization, it looks more natural. Of course, the optimization usually results in smaller motion sizes, but still, it can be better than manual adjustments because our optimization process optimizes for each area for each frame automatically. Okay, this is another example. Without optimization, you see some inconsistent perception around here, but after optimization, we get more natural results. Okay, to summarize, in this work, we propose a perceptual model that explains perceived quality and perceived deformation size in deformation lamps. And we validated the model in a psychophysical study. And we also developed two-pass optimization of motion vectors based on the perceptual model, which enabled us to apply our technique to an interactive application like motion retargeting. And if you're interested, please also come to our research demo, which is, but be careful, it is in an isolated room, so please don't miss it. Thank you for listening.
Thank you. Do you have any questions? Okay, so I'll start again. To what extent is your method dependent on the image quality metrics that you chose? Because if you say that you don't want to go over a given threshold, but if you used another method, then you may have other thresholds or whatever.
Yes, I tested some candidates. The first one is the whole process, including the linear gain and the contrast gain control. But when we remove the contrast gain control, then the prediction accuracy significantly decreases. So I think especially for the nonlinear process in the low-level visual mechanisms is quite important.
Okay. But there are also image quality metrics that take into account several levels of the human visual system, including low-level vision and more high-level?
Yes.
Did you try more complex metrics, if I can say so?
Yeah, actually, currently there's no available metrics for very higher level. So, but there's a deep learning methods. So maybe we can try such more complex models. It will be our future study. Thank you for that point.